textbook if you want to follow along. But our two major things today are central angles and their intercepted arcs. So a central angle, by definition, is an angle whose vertex is at the center of a circle. So here I've drawn a central angle, and the vertex is at the center of the circle. Okay? So this angle right here is considered a central angle. Now, an arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points in between. So this is an arc. This is also an arc. Any part of the circle can be called an arc. Okay? But this arc is special because do you see that this angle intercepts this arc? Kind of cuts that arc off. So this arc has the exact same measure as that central angle. So if this central angle is 110 degrees, what is the measure of this intercepted arc? 110 degrees. And we can go both ways with it. I could give you the arc, and you could give me the central angle because they're equivalent. They're the same. Now we have 3 different classifications for our arcs. We have minor arcs, major arcs, and then a special arc called a semicircle. You guys already know about a semicircle. How many degrees is a semicircle? 180. So a semicircle is exactly 180 degrees. Well, if it's less than 180, we call it a minor arc. So if the measure of the arc is less than 180 degrees, it's considered a minor arc. Now we name an arc. This is awesome. I like it when math makes sense. We name an arc with an arc symbol. Okay? So how would we read this? This reads, the measure of, the little m always means measure, the measure of arc AC is equivalent to the measure of angle ABC. Well, do you see ABC is a central angle? So the measure of this central angle is equivalent to the intercepted arc. Now, minor arcs can be named with 2 letters. So this is a minor arc. It appears to be maybe 70 degrees. It didn't say, but it's definitely less than 180, isn't it? So minor arcs can be named with 2 letters, whereas major arcs need 3. And we need that third one to let us know what direction we're going. So on this one, it says the measure of arc ADC. So from A through D, all the way to C. So that's that arc. And that's a major arc because it's greater than 180 degrees. So this arc can be found a couple ways, but one way, because this is the little arc we talked about a second ago, we could just do 360 minus this one. Does that make sense? And that would give us the measure of arc ADC. Semicircles are also named with 3 letters, so really the only arc that we would name with 2 letters is a minor arc. So if it has 2 letters, you know it's less than 180 degrees. All right. They're walking on the roof again.
Yeah.
It's like every day during 7th period. I wonder if somebody goes up there to exercise. You know, some of us go run the track. Some, I guess other people run on the roof. Yes.
Okay, so, like, could you name the minor arc with 3 letters?
You can.
Okay.
I can. If I stuck another little letter in here, I could name that ABC. But generally, minor arcs are named with 2. But major and semicircle must have 3. Yes, sir. Sure. Okay. I love geometry. Here we go again. It just makes sense. The arc addition postulate. Okay, what does that say? That says that the measure of an arc formed by 2 adjacent, so those are 2 connecting arcs, is the sum of the measures of the arc. This makes total sense. This big arc is the sum of the 2 small ones. Got it? All right, so how can we use that? We could use it on problems like this one in example 2. So my next slide has that enlarged. All right. So here's our picture, and it tells us that the measure of arc AB is 18 degrees. So this arc has a measure of 18 degrees. So if this is 18, then that central angle would also have to be 18. Now, what do we know about semicircles? They're 180. So this semicircle would be 180, and this semicircle would be 180, and this semicircle would be 180. We got them all over the place. Okay? So let's look at what they're asking us for. Find the measure of arc EAC. So the A tells us to get to C, we need to head in this direction. E to A to C. Okay. What is all of that? Well, we can approach this many different ways. But if this is a right angle right here, wouldn't that have to be a right angle? So if this little angle is 18, wouldn't it leave 72 degrees right there? Okay, and we also know that this arc EAB, is 180 degrees because it is a semicircle. So we would say 180 plus the 72 gives us 252. Now that's not the only way to work that problem, but that is one way. Alright, now let's do this arc, the measure of EC. So, let's see what that is. That is a minor arc. It's only 2 letters, so we have to go this direction. If it was the major arc, I'd have to give you more information, wouldn't I? Alright, so that's this one. Do you see that together the green and the pink make up the whole circle? So could I do 360 minus the 252? Yeah, that's one way. Or, because this is a diameter and this is a diameter, aren't those vertical angles?
Yes, that's what
Yeah. So if this is 18, wouldn't this have to be 18? So we could use arc addition also. And look what I get. The same thing. Any questions? Alright. Now, this is a whole bunch of, yeah, I get it, on this it's about to happen. Okay, in a circle, or if we have congruent circles. How do we know we have congruent circles? They have congruent what?
Radii.
Radii, very good. So, in a circle or congruent circles, congruent central angles have congruent chords. Okay, so if we have congruent central angles, then this chord is congruent to this chord. Okay, and we're going to prove that in a minute, why that has to be true. Let's go ahead and prove it. Alright, so let's prove that if we have congruent central angles, we have congruent chords. So, step 1, angle BAC is congruent to angle DAE. What was that? Given. Okay, step 2, AB is congruent to AD, and AC is congruent to AE. They are all radii. Very good. And we know that all radii of a circle are congruent. Yeah. Alright, now I see some, triangle congruent statements.
Time to cry.
No, it's not. It's time to get excited. Because this is congruent to this, and this is congruent to this, are actually all congruent to each other. This would be side, angle, side, side, angle, side, side, angle, side, happiness. Okay? Now, if we have congruent triangles, then we know that corresponding parts of congruent triangles are congruent.
Oh,
C. Okay. So, there's the proof. There's the proof for this. So, if we have congruent central angles, those chords that connect those angles are also congruent. Now, if we have congruent chords, then we have congruent arcs. So they showed it here, but it would also work if we just had it like this, over here. And if I told you that this arc is congruent to this arc, this chord is congruent to this chord, then what we know is this arc is congruent to this arc. Correct, if it's the same circle, or congruent circles. The last one, congruent arcs have congruent central angles. So that's if they tell us this arc is congruent to this arc, then this angle would have to be congruent to that angle. Okay? Alright, and all these things we can use to solve for missing measures. It's nice. Alright, so we just did this one. Alright, let's do this one. If RS is congruent to TU, so this chord is congruent to this chord, find the measure of arc RS. This was segment, that's the chord. This is arc, that's this. Well, we have congruent chords, so we also know we have congruent arcs. So we know that 3x would have to equal 2x plus 27. So x is 27, and that is not my answer. All I did was move that over. Okay? So to find RS, we would multiply that 27 times 3. So the measure of arc RS is 81 degrees. Okay. Alright, now, this one. In a circle, if a radius or diameter is perpendicular to a chord, so a radius perpendicular to a chord, then it bisects the chord and its arc. So it bisects that and it bisects the arc. Yes, sir.
So are we going to be doing circle proofs?
Oh, yeah.
Great.
I am not going to cheat you of the opportunity to do some awesome proofs. All right. There's excitement in the room right now. Everybody is giddy about the opportunity to do more proofs. I understand. I'm right there with you. I hear the excitement. All right. So here we go. In a circle, the perpendicular bisector of a chord has to be the radius or the diameter. So if we had a circle, and I can't really draw a circle, so I cheat. Okay? If we have a chord, and whenever we know there is a line that bisects and is perpendicular, then we know it must pass through the center. Yes, it has to be the diameter. That's what this one says. Yep. Okay, and then how can we use some of these concepts? Alright, so if we have a radius perpendicular to a chord, we know it bisects the chord. Right?
Right.
Now, this radius is not drawn in, but do you see when I draw it in, I've created a beautiful right triangle. And if this radius has a length of 5, what does this radius have a length of? 5. And then we're all excited because it's one of our favorite Pythagorean triangles. It's a 3, 4, 5. Yes. Yes. That is 4. So what is the length of BD? BD has a length of 8. Now, how did I know, guys from yesterday, how did I know this is asking for the length of a segment? Okay, what do you think?
Because the line over the top.
Right. It does not have the segment bar over it. When it has a segment bar, we're just naming the chord. Without that bar, we're asking for the length. Beautiful. All right, so as soon as you finish, you're just killing it on this terrific 10, because I know you're going to. You can jump to your bookworks. Now, for some reason, On the calendar I gave you, there's a comma right here. I don't know why, it shouldn't be there. So this little last bit is 47 through 49. Okay? All right, and that's it. Terrific 10 time.
Can you remember that?
Sure.